everyone, welcome back to my channel. In this video, we are going to study about Euler's theorem for homogeneous function. To understand the concept of Euler's theorem, first let us understand what is homogeneous function. The definition of homogeneous function says, if every term of the function is of same degree, then the function is called homogeneous function of that degree. Let us explain with an example. F of x, y, z, which is equal to 3x square yz plus 5 into x y square z plus 4 into z power 4. In this equation, here every terms of the equation is of same degree. Here first term is 3x square yz. Here we have a degree 4, that is x square yz is of the degree 4. Here consider the second term, that is 5x into y square z. Here also we have the degree 4. Here also degree 4. So the definition of the homogeneous function says, if every terms of the function is of same degree, then that function we can call it as homogeneous function of that degree. In general, we can take f of x, y, which is equal to a naught x power n plus a1 into x power n minus 1 into y plus a2 x power n minus 2 into y square plus up to the term an into, here last term is x power n minus n. N minus n is 0, hence x power anything to the power 0 is 1. Hence we can take last term as an into y power n. This is a function. In that case, to obtain a general equation of homogeneous function, if we take x power n common in this equation, we can take it as x power n into, here in the first term the remaining is a naught plus, here x power n minus 1 we can split it as x power n into x power minus 1 and take x power n outside the bracket, the remaining is a1 into, here x power minus 1 if we take to the denominator, that becomes y by x plus a2 into, here also same, x power n minus 2 we can split it as x power n into x power minus 2 and take x power n outside the bracket, the remaining will be a2 into y by x whole square plus and so on, an into, here in the last term we have no x power n term, so multiply and divide by x power n and take x power n outside the bracket, the remaining is an into y by x whole power n. Simply we can take this as x power n into, here this is an equation of the form f of y by x, that is f of x, y, which is equal to x power n into f of y by x. This is a general equation to represent homogeneous function. This is about homogeneous function definition and example. Now let us understand the Euler's theorem for homogeneous function. In the examination, they may ask, state and prove Euler's theorem on homogeneous function. Euler's theorem is stated as, if u is equal to x power n into f of y by x is a homogeneous function of degree n, here this is a homogeneous function of degree n which contains x and y, then x into del u by del x plus y into del u by del y, which is equal to n into u. Here we have to show that x into del u by del x plus y into del u by del y value, that is equal to n into u, where n is nothing but degree for the homogeneous function u. For that, first you have to consider the homogeneous function u, then we have to consider the LHS of the equation and we have to show that that equation which is equal to n into u. That is a proof of the Euler's theorem. First consider the given homogeneous equation u is equal to x power n into f of y by x. Call this as equation number 1. First step we have to find del u by del x and del u by del y. Here del u by del x and del u by del y are partial derivative of u with respect to x and y. So what's the first step? We have to differentiate equation 1 partially with respect to x. We get del u by del x as, here del u by del x which is equal to, here we have to differentiate this u partially with respect to x. So here x power n and f of y by x both are function. So we have to apply product rule over here. Consider x power n as first function and f of y by x as second function. We get as first function into derivative of f of y by x is f dash of y by x into, again we have to differentiate this y by x, that is y is constant, take as it is, into differentiation of 1 by x is minus 1 by x square plus second function, that is f of y by x into differentiation of x power n is n into x power n minus 1. This is our del u by del x. Next you have to multiply del u by del x by x. We get as x into del u by del x which is equal to, here if we multiply x for this and here also for the x, we get as x power n into x is x power n plus 1. Here also x square term, so if we take x square to the numerator, that becomes x power minus 2. Here we have x power n plus 1, here x power minus 2. So bases are same. If we add the powers, hence we get minus x power n minus 1 into y into f dash of y by x plus, here also we have to multiply by x, that is x power n minus 1 into x, that is x power plus 1. So we get as x power n minus 1 plus 1, here plus 1 minus 1 gets cancelled, the remaining is x power n itself. So for this term we get as n into x power n into f of y by x. If we multiply x to the del u by del x value, we get as, for the first term if we multiply by x, that is x power n into x, we get as x power n plus 1. If we take x squared to the numerator, that becomes x power minus 2. So bases are same, adding the powers we get as x power n plus 1 minus 2, we get as x power n minus 1 into y into f dash of y by x, that is minus of that value, plus here also x power n minus 1 into x power 1, we get as x power n. So n into x power n into f of y by x. This is our x into del u by del x value. Call this as equation number 2. Next step, we have to find y into del u by del y. For that, we have to differentiate equation 1. Here, partial differentiation of u with respect to y is del u by del y, which is equal to, here x power n is constant, take as it is, into differentiation of f of y by x is f dash of y by x into, again we have to differentiate this y by x term, that is 1 by x is constant, into differentiation of y is 1. Here del u by del y, which is equal to, here x power n into, if we take 1 by x, that is x to the numerator, that becomes x power n minus 1. So that is del u by del y, which is equal to x power n minus 1 into f dash of y by x. Next step, we have to multiply by y both the side of the equation. We get as y into del u by del y, which is equal to y into x power n minus 1 into f dash of y by x. Call this as equation number 3. Next step, by adding equation 2 and equation 3, we get the value as, here first term is x into del u by del x, second term is plus y into del u by del y, which is equal to, here x into del u by del x is minus x power n minus 1 into y into f dash of y by x plus n into x power n into f of y by x plus y into del u by del y value is y into x power n minus 1 into f dash of y by x. Here observe carefully, here this we get the value as minus sign of x power n minus 1 into y into f dash of y by x. Here positive sign of y into x power n minus 1 into f dash of y by x gets cancelled. The remaining is n into x power n into f of y by x. This is the value of x into del u by del x plus y into del u by del y. We know that from equation 1 we have u is equal to x power n into f of y by x. So in the place of x power n into f of y by x, we can take it as u. Hence, we get the Euler's theorem value as x into del u by del x plus y into del u by del y, which is equal to n into u. So this is the equation of Euler's theorem for homogeneous function. This completes the proof. Here we have another theorem to be proved with the help of Euler's theorem. Here is a statement: if u is equal to f of x comma y is a homogeneous function of degree n, then x square into del square u by del x square plus 2xy into del square u by del y into del x plus y square into del square u by del y square, which is equal to n into n minus 1 into u. This is a statement. We have to show that for the homogeneous function u is equal to f of x comma y, we have to show that x square into del square u by del x square plus 2xy into del square u by del y into del x plus y square into del square u by del y square value, which is equal to n into n minus 1 into u, where n is nothing but a degree for a homogeneous function u. Here we have to show this equation with the help of Euler's theorem. So first consider, by Euler's theorem we have x into del u by del x plus y into del u by del y value, which is equal to n into u. We already proved this equation. Here LHS of this statement as, here they have second order derivative of u with respect to x and y. So this is a Euler's theorem. Call this as equation number 1. First step, we have to differentiate this equation 1 partially with respect to x. We get the value as, here left hand side, here x and del u by del x both are functions, so we have to apply product rule for this. We get the value as, first function into differentiation of del u by del x is del square u by del x square plus second function, that is del u by del x into differentiation of x is 1 plus y is constant, take as it is, into here del u by del y. We have to differentiate this equation with respect to x. We get the value as del square u by del x into del y. First you have to take del x term, then we have to take this del y as it is. To differentiate del u by del y partially with respect to x, we get the value as del square u by del x into del y, which is equal to, here n is constant, take as it is, into, here differentiation of u is del u by del x. Next step, here del u by del x, if we take this positive term to the right hand side, that becomes x into del square u by del x square plus y into del square u by del x into del y, which is equal to, if we take to the right hand side, that becomes n into del u by del x minus del u by del x. If we take del u by del x as common, we get as n minus 1 into del u by del x. Next step, here multiply throughout the equation by x, we get the value as x square into del square u by del x square plus x into y into del square u by del x into del y, which is equal to n minus 1 into x into del u by del x. Call this as equation number 2. In the similar way, we have to differentiate equation 1 partially with respect to y. We get as, here equation 1 is x into del u by del x plus y into del u by del y, which is equal to n into u. If we differentiate this equation partially with respect to y, means here x is constant, take as this into, here differentiation of del u by del x with respect to y means del square u by del y into del x plus, here y and del u by del y both are functions, so we have to apply product rule for this. That is, first function into derivative of del u by del y is del square u by del y square plus second function into differentiation of y is 1, which is equal to, here n is constant, take as this, into differentiation of u with respect to y is del u by del y. Next step, we have to take this value to the right hand side. We get the value as x into del square u by del y into del x plus y into del square u by del y square, which is equal to, if we take del u by del y to the right hand side and take del u by del y as common, we get as n minus 1 into del u by del y as before. In next step, we have to multiply throughout the equation by y. We get the value as x into y into del square u by del y into del x plus y into y is y square into del square u by del y square, which is equal to n minus 1 into y into del u by del y. Call this as equation number 3. Next step, adding equation 2 and equation 3, we get the value as, by adding equation 2 and equation 3, we get equation 2 is x square into del square u by del x square plus xy into del square u by del x del y plus equation 3 is xy into del square u by del y del x plus y square into del square u by del y square, which is equal to n minus 1 x into del u by del x plus n minus 1 y into del u by del y. We know that we studied in a partial derivative del square u by del x del y is same as that of del square u by del y into del x. We studied previously. So substituting that value here, we get x square into del square u by del x square plus 2xy, that is xy into del square u by del x into del y, we can write it as del square u by del y del x. So if we add these two terms, we get as 2xy into del square u by del y del x plus y square into del square u by del y square, which is equal to, here x plus, in the right hand side, if you take n minus 1 as common, we get as n minus 1 into x into del u by del x plus y into del u by del y. Here we can take n minus 1 as common for this, so we get n minus 1 into x into del u by del x plus y into del u by del y. We know that x into del u by del x plus y into del u by del y value, that becomes n into u. Substitute this value as nu. We get as x square into del square u by del x square plus 2xy into del square u by del y into del x plus y square into del square u by del y square, which is equal to, here n minus 1 into n into u. So we get the value as x square into del square u by del x square plus 2xy into del square u by del y into del x plus y square into del square u by del y square, which is equal to n into n minus 1 into u. This completes the proof. This is very important formula to remember, that is x square into del square u by del x square plus 2xy into del square u by del y into del x plus y square into del square u by del y square value, that is equal to n into n minus 1 into u. Next, we can solve some problems related to Euler's theorem of a homogeneous function. In problems on Euler's theorem, we have three types of problems here. Take the first type of problems. Verify Euler's theorem for f of x, y, z, which is equal to 3x square yz plus 5xy square z plus 4z power 4. Take the given problem. Here, we have to verify the Euler's theorem for the function this here. To verify Euler's theorem, first step we have to find if the given function is homogeneous function or not. We know that homogeneous function is defined by f of x comma y is x power n into f of y by x. That is, homogeneous function is of the form x power n into f of y by x. Here we have to see we can reduce this to the form x power n into f of y by x or not. Here 3x square yz plus 5x y square z plus 4z power 4. In this equation, if we take x power 4 as common, we get the value as x power 4 into, here we have only x square term. To obtain x power 4 means we have to multiply and divide by x square. We get as in the numerator x square into x square is x power 4. In denominator we have x into x. So we can write it as x power 4 into 3 into, here we have in the denominator we have yz divided by x square. So we can split it as y by x into z by x plus 5 into, here also if we multiply and divide by x cube, so we get in the numerator x into x cube is x power 4. So we can take outside the bracket. In the denominator we get the value as x cube, that is, we can split it as x square into x. So we can write it as 5 into y by x whole square into z by x plus, here also here we have z power 4. So multiply and divide by x power 4, we get as in the numerator we can take common as x power 4 and the remaining is 4 into z by x whole power 4. So we have to reduce this to the form x power n into f of y by x. For that we have to consider this like this. Now we can take it as this is of the form x power 4 into f of, this is a function of the form y by x and z by x. So we can simply write it as x power 4 into f of y by x comma z by x. This is a very important step to see if it is a homogeneous function or not. Take here as a maximum value here x square yz. So we have to take the common value as x power 4. Here if in the place of x square yz we have x cube yz, we have to take the common value as x power 5. We have to note carefully. So taking x power 4 common means we have to multiply and divide by some values. So we get the equation of the form f of x comma y comma z, which is equal to x power 4 into f of y by x comma z by x. So we can conclude that this is a homogeneous function of degree n is equal to 4. Here x power n, so n is of a degree for a homogeneous function. So we can take n value which is equal to 4. So by Euler's theorem we have, for the Euler's theorem for the function x, y, z, this is a formula, that is x into del f by del x plus y into del f by del y plus z into del f by del z value which is equal to n into f. Here n value is 4 into f. That means to verify Euler's theorem for this function means we have to show that the value, that is x into del f by del x plus y into del f by del y plus z into del f by del z value which is equal to 4 into f, that is function of x comma y comma z. We have to show that LHS which is equal to value 4 into f. This is a procedure to verify Euler's theorem. This is a first type of problem to verify Euler's theorem. That means first step we have to find it is a homogeneous function or not. Using that we can find the degree, that is n value. After finding n value, take the Euler's theorem. We have to show that Euler's theorem value which is equal to n into u. Here Euler's theorem for the standard function we have derived is x into del u by del x plus y into del u by del y which is equal to n into u for the function of x and y. Here we have f of x comma y comma z. So we have to apply Euler's theorem for x, y, z as x into del f by del x plus y into del f by del y plus z into del f by del z which is equal to n into f, where n is nothing but 4. Take the LHS of the equation. LHS is equal to x into, here del f by del x is nothing but we have to differentiate this f partially with respect to x. We get a value as del f by del x, that is partial differentiation of f with respect to x is 3 into differentiation of x square is 2x. So we get 2 into 3 is 6x into y z is constant, take as it is, plus here differentiation of x is 1. So the remaining is 5y square z. This value becomes 0 plus similarly y into del f by del y value means we have to differentiate this equation partially with respect to y. Here 3x square z is constant, take as it is, into differentiation of y is 1. Here we have y term, that is differentiation of y square is 2y, that is 5 into 2 is 10. Hence we get y into 3x square z plus 10xyz. Here no y term, so becomes 0 plus z into here del f by del z, that is differentiate f with respect to z we get as here 3x square y is constant, take as it is, into differentiation of z is 1 plus here 5xy square is constant, take as it is, into differentiation of z value is 1 plus 4 into differentiation of z power 4 is 4z cube. Hence we get 4 into 4 is 16z cube. This is a LHS of the equation. Next step, multiply xyz inside the bracket and simplify. We get the value as 6x square yz plus 5xy square z plus 3x square yz plus 10xy square z plus 3x square yz plus 5xy square z plus 16z power 4. Now here we have 6x square yz plus 3x square yz plus 3x square yz. We get the value as 12x square yz plus here 5xy square z. Here we have 10xy square z. Here we have 5xy square z. Hence we get 20xy square z plus here the remaining is 16z power 4. So in this equation we can, if we take common as 4, we get as 4 into 3x square yz plus 5xy square z plus 4z power 4. So this is a value of f of x comma y comma z, that is 3x square yz plus 5xy square plus 4z power 4. Hence we can conclude that this is of the form 4 into f of x comma y comma z. This is a RHS of Euler's theorem. Hence we have verified the Euler's theorem, that is x into del f by del x plus y into del f by del y plus z into del f by del z value, which is equal to 4 into f of x comma y comma z. This completes the problem. We shall move on to another problem so that you can understand in a better way. Verify Euler's theorem for the function u is equal to x cube minus 2x square y plus 3xy square plus y cube. Here first take the given problem, that is u of x comma y, which is equal to x cube minus 2x square y plus 3xy square plus y cube. Here this is a equation of the form u of x comma y. Here first step we have to reduce this equation to homogeneous equation form. For that take x cube as common, we get as x cube into 1 minus, here to take x cube as common means here only we have x square term. So multiply and divide by x term, we get as x into x is x cube. Take x cube outside the bracket, remaining is minus 2 into here y by x plus here only x term, so multiply and divide by x square. In the numerator we have x cube, so we can take outside the bracket. The remaining is 3y by x whole square plus here no x cube term, so multiply and divide by x cube. So we get as, if you take x cube outside the bracket, remaining is y by x whole cube. So this is of the form x cube into u of y by x. So u of x comma y comma z, which is equal to x cube into u of y by x. So this is a homogeneous equation of degree n, that is equal to 3. So we get the value of n as 3. So by Euler's theorem we have x and y term. Euler's theorem is x into del u by del x plus y into del u by del y, which is equal to n into u, where n is nothing but 3 into u. That is, to verify Euler's theorem means we have to show that LHS of this Euler's theorem, which is equal to 3 into u. For that, consider LHS of the equation, that is LHS is equal to, here x into del u by del x is, here we have to differentiate this u term with respect to x partially. We get as x into, differentiation of x cube is 3x square minus, here 2 into y is constant, take as it is, into differentiation of x square is 2x. Hence we get 2 into 2 is 4xy. Plus 3y square is constant, take as it is, into differentiation of x is 1. So we get 3y square plus here no x term, so we get the value as 0 plus y into here del u by del y is, we have to differentiate this equation partially with respect to y. Here no y term, so we get the value as 0 minus 2x square is constant, take as it is, into differentiation of y is 1 plus 3x take as constant, into differentiation of y square is 2y. So 2 into 3 is 6xy plus differentiation of y cube is 3y square. This is the LHS of the equation. Next step we have to multiply x and y inside the bracket and simplify. We get as x into 3x square is 3x cube minus 4 into x is x square y plus 3y square into x is 3xy square plus y into minus 2x square is minus 2x square y plus 6xy into y is 6xy square plus 3y square into y is 3y square. This is LHS. Here minus 4x square y, here we have minus 2x square y. So here minus 4x square y minus 2x square y means minus 6x square y. Remaining as it is, that is 3x cube minus 6x square y plus here we have 3xy square. Here we have plus 6xy square, hence we get 9xy square plus 3y cube as it is. So in this equation we can take 3 as common. We get as 3 into x cube minus, if we take 3 as common, the remaining is 2x square y plus here also if we take 3 as common, remaining is 3xy square plus y cube. So this is of the form 3 into u of x comma y. Hence we verified the Euler's theorem, that is x into del u by del x plus y into del u by del x. This is LHS of the equation, which is equal to RHS is 3u of x comma y. Hence this verifies Euler's theorem. This completes the problem. We shall move on to another problem. Verify Euler's theorem for the function u is equal to x power 4 into log of y by x. Consider the given problem. Here this is an equation of the form homogeneous function. This is already of the form homogeneous function. So it is a homogeneous function of degree 4. Here x power n. Here n is of 4. Hence this is a homogeneous function of degree 4. So to verify Euler's theorem, we have x into del u by del x plus y into del u by del y, which is equal to n into u, where n is nothing but 4 into u. You have to show that LHS of equation, which is equal to 4 into u. Consider LHS value, that is x into del u by del x, that is differentiation of u with respect to x partially, we get as here x power 4 and log of y by x, both are function. So we have to apply product rule. First function into derivative of log of y by x. We know that differentiation of log x is 1 by x. Here in the place of x we have y by x. So we get as 1 by x, that is 1 by y by x, we can take it as x by y, into, again we have to differentiate this y by x term, that is y is constant, take as it is, into differentiation of 1 by x is minus 1 by x square, plus second function, that is log of y by x, into differentiation of x power 4 is 4x cube, plus y into del u by del y, that is differentiation of u with respect to y partially, we get as y into, here differentiation of u is here x power 4 is constant, take as it is, into differentiation of log of y by x is here 1 by y by x, into, again we have to differentiate this y by x term, that is 1 by x is constant, take as it is, into differentiation of y is 1. So we get as this. In numerator we have x power 4, here we have x square, so x square gets cancelled, y term gets cancelled, here also y term gets cancelled, and this x terms gets cancelled. We get the value as, multiply xy and y term inside the bracket, we get value as, here x into, here x square gets cancelled, the remaining is x square into x is x cube into x, that is x power 4, that is minus x power 4, plus multiply x inside the bracket, we get as 4 into x cube into x is x power 4 into log of y by x, plus here y gets cancelled, x also gets cancelled, the remaining is x power 4. So minus x power 4 plus x power 4 gets cancelled, the remaining is 4x power 4 into log of y by x, that is which is equal to 4 into, here x power 4 into log of y by x is nothing but u, hence we get 4 into u, which is equal to RHS of the equation. Hence we verified Euler's theorem as x into del u by del x plus y into del u by del y value, which is equal to 4 into u. U is nothing but x power 4 into log of y by x. This completes the problem. So this is the first type of problem on Euler's theorem, that is to verify the Euler's theorem for the given function. This is a procedures. Next we shall move on to another type of problem. If u is equal to sine inverse of x square plus y square divided by x plus y, prove that x into del u by del x plus y into del u by del y, which is equal to tan into u. Previously we have to verify Euler's theorem, but here we have to prove that x into del u by del x plus y into del u by del y value, which is equal to tan u. First consider the given problem. Here u is equal to sine inverse of x square plus y square divided by xy. To make the simplification easy, consider this value which is equal to z, which is equal to, if we take this sine inverse to the left hand side, that becomes sine u, which is equal to x square plus y square divided by x plus y. This is a procedure to solve this type of problem. Here they have mentioned u is equal to sine inverse of x square plus y square by x plus y. Consider this equation as z, which is equal to, if we take sine inverse to the left hand side, that becomes sine u, which is equal to x square plus y square by x plus y as it is. Next step, we have to reduce this to the homogeneous equation form. For that, the procedure is same as before. Here in the numerator, if we take x square as common, and in the denominator if we take x as common, we get as x square into, the remaining is 1 plus, if we take x square common means you have to multiply and divide by x square, so we get as y by x whole square divided by, if we take x as common, the remaining is 1 plus, here simply y, so we have to multiply and divide by x, we get as y by x. Here x square by x we can cancel 1x, the remaining is x itself. So the equation reduced to the form x into, here numerator is of the form 1 plus y by x whole square, denominator is 1 plus y by x. So this is a function of the form y by x. We can simply write it as f of y by x, that is our sine u value. that is z which is equal to sin u which is equal to x into f of y by x. So we can conclude that this is a homogeneous function of degree 1. Here x power 1, so n value which is equal to 1. So we can conclude that this is a equation that is homogeneous function of degree 1. Next step, to prove that x into del u by del x plus y into del u by del y value which is equal to tan u. By Euler's theorem, we get the value as x into del z by del x plus y into del z by del y which is equal to n into z. This is because we are considering this equation value as z. So we have to apply Euler's theorem for the function z itself. So we get as x into del z by del x plus y into del z by del y value which is equal to n into z. This is our Euler's theorem. So we get, we substitute z value as this, that is z is nothing but sin u. Hence we can substitute the value as x into del of sin u by del x plus y into del of sin u by del y which is equal to, here n value is 1 into z is nothing but sin u. Understand carefully, we have considered this equation as z, so that z value which is equal to, if we take sin inverse to the left hand side, we get z value as sin u which is equal to this. So this is the equation reduced to the form homogeneous function. So we have to consider the Euler's theorem for the function z. We get as x into del z by del x plus y into del z by del y which is equal to n into z, where our z is nothing but sin u. Substitute z value as sin u, here we get this. Next step, we have to differentiate this sin u with respect to x. Here also we have to differentiate this sin u with respect to y. We get the value as del u by del x and del u by del y, that is x into, here differentiation of sin u with respect to x is, here differentiation of sin u is cos u, into, again differentiation of u with respect to x is del u by del x plus y into, here differentiation of sin u with respect to y is cos u into differentiation of u with respect to y is del u by del y which is equal to sin u. Here also cos u term, here also cos u term. If we take cos u as common and that cos u goes to the right hand side, that becomes x into del u by del x plus y into del u by del y which is equal to, if we take cos u to the right hand side, that becomes divided by cos u, that is sin u by cos u. We know that sin u by cos u value is tan u. Hence we can prove that x into del u by del x plus y into del u by del y value which is equal to tan u. This completes the problem. We shall move on to another problem so that you can understand in a better way. If u is equal to sin inverse of root x plus root y divided by root x minus root y, prove that x into del u by del x plus y into del u by del y value which is equal to 0. First step, take the given function as z, that is z is equal to, if we take sin inverse to the left hand side, that is sin u which is equal to root x plus root y by root x minus root y. Next step, to reduce this to the homogeneous function form, take root x common in both numerator and denominator. We get as root x common means remaining is 1 plus, here root of y by x divided by, here also root x common means the remaining is 1 minus root of y by x. If we cancel this root x term, there will be no x power terms. So take this root x to the numerator. Here root x is nothing but we can take it as x power 1 by 2. Here also x power 1 by 2. This, if we take this to the numerator, that becomes x power minus 1 by 2. So the bases are same. If we add the powers, the remaining is x power 0. Hence we get the value as x power 0 into, here this is the equation of the form f of y by x. So the equation reduced to homogeneous equation. Hence we can conclude that this is a homogeneous function of degree 0. Here n value is 0. So this is a homogeneous function of degree 0. So we can substitute in the place of n as 0. Hence by Euler's theorem we have x into del z by del x plus y into del z by del y which is equal to n into z. Here this is an important step. We have to consider the Euler's theorem for the function z, not for u. This is a Euler's theorem for the function z, because we have the function z is equal to sin u which is equal to root x plus root y by root x minus root y. So substitute z value as sin u. Next step we get as x into del of sin u by del x plus y into del of sin u by del y which is equal to, here n value is 0 into z is sin u. Here differentiating sin u with respect to x and y and simplify, we get as x into differentiation of sin u is cos u into del u by del x plus y into differentiation of sin u is cos u into del u by del y which is equal to 0. If we take cos u as common and that cos u goes to the right hand side, that becomes x into del u by del x plus y into del u by del y which is equal to 0. Here 0 divided by cos u, that becomes 0 itself. So this is a type 2 problems on Euler's theorem, that is they have given the values, that is u is equal to some values. We have to prove that Euler's theorem, that is x into del u by del x plus y into del u by del y value, which is equal to some values. This is a type 2 problems. We shall move on to type 3 problems on Euler's theorem. If u is equal to tan inverse of x cube plus y cube by x plus y, prove that x square into del square u by del x square plus 2xy into del square u by del x del y plus y square into del square u by del y square value, which is equal to 2 cos 3u into sin u. Second, we have to prove that x square into del square u by del x square plus 2xy into del square u by del x del y plus y square into del square u by del y square, which is equal to 1 minus 4 into sin square u into sin 2u. This is another type of problem. Consider the given problem, that is u is equal to tan inverse of x cube plus y cube by x plus y. As before, we have to consider this value as z, which is equal to, if we take tan inverse to the left hand side, that is tan u, which is equal to x cube plus y cube by x plus y. First step, we have to reduce this to homogeneous function form. We already know to reduce to homogeneous function form, we have to take the common factor as this, that is, if we take x cube as common in numerator and x as common in denominator, we get as x cube into 1 plus here y by x whole cube by x into 1 plus y by x. Here x cube, x gets cancelled, the remaining is x square into, here this is of the form f of y by x. So we can conclude that this is a homogeneous function of degree 2. Hence we get n value as 2. So we get from Euler's theorem, we get the value as x into del z by del x plus y into del z by del y, which is equal to n into z. Substituting z value as tan u, we get as x into del of tan u by del x plus y into del of tan u by del y, which is equal to, here n value is 2 into z value is tan u. Here differentiation of tan u with respect to x is secant square u, hence we get x into secant square u into, again differentiation of u with respect to x is del u by del x plus y into differentiation of tan u is secant square u into differentiation of u with respect to y is del u by del y, which is equal to 2 into tan u as it is. Next step, we have to take secant square u outside the bracket, we get as secant square u into x into del u by del x plus y into del u by del y, which is equal to 2 into tan u. Take secant square u to the right hand side, that becomes x into del u by del x plus y into del u by del y, which is equal to 2 into tan u divided by secant square u. We know that tan u we can write it as sin u by cos u, and 1 by secant square u is cos square u. That is x into del u by del x plus y into del u by del y, which is equal to 2 into, here tan u is sin u by cos u into, here 1 by secant square u, that is reciprocal of secant square u is cos square u, hence we get cos square u. Here cos u gets cancelled, the remaining is here 2 into sin u into cos u. This is of the form, that is sin 2x is 2 sin x into cos x. So we can write it as sin 2u, that is x into del u by del x plus y into del u by del y, which is equal to sin 2u. Here we have to observe that this problem is of the form, we already discussed the second proof, that is x square into del square u by del x square plus 2xy into del square u by del y into del x plus y square into del square u by del y square, which is equal to n into n minus 1 into u. We can solve this problem using two methods. First method is, after finding x into del u by del x plus y into del u by del y, which is equal to, that is sin 2u. Next step, as we derive this equation, next step, if we differentiate this equation partially with respect to x and y and multiply x and y inside the bracket and simplify, we get the value. Or we can apply another formula, that is, we have to remember this formula, that is homogeneous equation of degree n is given by the formula x square into del square u by del x square plus 2xy into del square u by del y into del x plus y square into del square u by del y square, which is equal to g of u into g dash of u minus 1. We have to remember this formula. Now I will use this method to solve this problem. Here, after obtaining x into del u by del x plus y into del u by del y, which is equal to some value, that is sin 2u, call this value as g of u. Next, to find the value, that is, we have to show that first one is x square into del square u by del x square plus 2xy into del square u by del y into del x plus y square into del square u by del y square value we have to prove. So consider this formula and simplify, we get as x square into del square u by del x square plus 2xy into del square u by del y into del x plus y square into del square u by del y square, which is equal to, here substituting this value as g of u into g dash of u minus 1. Here g of u is sin 2u into g dash of u is, you have to differentiate this sin 2u with respect to u, we get as 2 into cos 2u minus 1 as it is. Next step, multiply sin 2u inside the bracket, we get as 2 into sin 2u into cos 2u minus sin 2u into 1 is sin 2u. We know that 2 sin 2u into cos 2u, this is of the form sin 2x, that is sin 2x is 2 sin x cos x. Here in the place of x we have 2u, hence we get the value as sin 4u minus sin 2u as it is. Here sin 4u minus sin 2u, this is of the form sin c minus sin d. We know that sin c minus sin d, we can write it as 2 cos of c plus d by 2 into sin of c minus d by 2. Here c is 4u and d is 2u. Substituting these values here, we get as x square into del square u by del x square plus 2xy into del square u by del y into del x plus y square into del square u by del y square value as. Here substituting c value as 4u and d value as 2u, we get as 2 cos of 4u plus 2u by 2 is 4u plus 2u is 6u by 2. Hence we get as 2 cos 3u into sin of 4u minus 2u by 2. That is 4u minus 2 is 2u by 2 is u itself. Hence we get the value as 2 cos 3u into sin u. We have shown that x square into del square u by del x square plus 2xy into del square u by del y into del x plus y square into del square u by del y square value, which is equal to 2 cos 3u into sin u. In the similar way, we have to prove second one, that is x square into del square u by del x square plus 2xy into del square u by del y del x plus y square into del square u by del y square, which is equal to, here g of u is sin 2u into g dash of u is 2 cos 2u minus 1. Now we know that from trigonometric formula, cos 2x in terms of sin, we can write it as 1 minus 2 sin square x. That is cos 2x is equal to 1 minus 2 sin square x. Here in the place of x we have u. Substituting the value cos 2x here, we get as sin 2u into 2 into, in the place of cos 2u we can substitute as 1 minus 2 sin square u minus 1. Here multiplying 2 inside the bracket and simplify, we get as sin 2u into 2 into 1 is 2 minus 2 into 2 is 4 sin square u minus 1. Here 2 minus 1 is 1. Hence we get x square into del square u by del x square plus 2xy into del square u by del y into del x plus y square into del square u by del y square, which is equal to sin 2u into the 2 minus 1 is 1 minus 4 sin square u. This completes the problem. We shall move on to another problem. If u is equal to cos inverse of x cube plus y cube by x plus y, prove that x square into del square u by del x square plus 2xy into del square u by del x del y plus y square into del square u by del y square, which is equal to minus 2 cot u minus 4 cot cube u. First take the given problem. Z is equal to, if you take cos inverse to left hand side, that becomes cos u, which is equal to x cube plus y cube by x plus y. Take x cube as common in numerator and x as common in denominator and simplify, we get as x cube into 1 plus y by x whole cube by x into 1 plus y by x. Here x gets cancelled. We get the value x square into f of y by x. So this is of the form homogeneous function where n is equal to 2. Z is equal to x square into f of y by x is a homogeneous function of degree 2. Hence n value which is equal to 2. Therefore, by Euler's theorem, we get x into del z by del x plus y into del z by del y, which is equal to n into z. Substituting z value and n value, we get x into del of cos u by del x plus y into del of cos u by del y, which is equal to 2u, where n is 2, z is cos u. Next, we have to differentiate cos u with respect to x and with respect to y. Partially, we get as x into differentiation of cos u is minus sin u into differentiation of u is del u by del x plus y into differentiation of cos u is minus sin u into del u by del y, which is equal to 2 cos u as it is. Take minus sin u outside the bracket and that minus sin u goes to the right hand side, that becomes x into del u by del x plus y into del u by del y, which is equal to minus 2 cos u divided by sin u. We know that cos u by sin u is cot u, hence we get x into del u by del x plus y into del u by del y, which is equal to minus 2 cot u. So this is our g of u. After obtaining x into del u by del x plus y into del u by del y, we have two methods. One is using theorem. Another one is x square into del square u by del x square plus 2xy into del square u by del y into del x plus y square into del square u by del y square value, which is equal to g of u into g dash of u minus 1. So this is our g of u. Next we have to find g dash of u and substitute in this equation, we get the value of this, that is x square into del square u by del x square plus 2xy into del square u by del y into del x plus y square into del square u by del y square, which is equal to, here g of u is minus 2 cot u, g dash of u is nothing but differentiating g of u with respect to u, hence we get differentiation of cot u is minus cosecant square u, so we get here minus into minus plus 2 into cosecant square u as it is minus 1. Next step, we know that cosecant square u is of the form 1 plus cot square x. We know that cosecant square x we can write it as 1 plus cot square x to obtain the right hand side of the problem. So substituting that value we get minus 2 cot u into 2 as it is into, in the place of cosecant square u we have to substitute 1 plus cot square u minus 1. Multiply 2 inside the bracket we get as minus 2 cot u, which is equal to, here 2 into 1 is 2 minus 1 is 1 plus 2 into cot square u is 2 cot square u. Multiplying minus 2 cot u inside the bracket we get as x square into del square u by del x square plus 2xy into del square u by del y into del x plus y square into del square u by del y square, which is equal to minus 2 cot u into 1 is minus 2 cot u plus into minus minus 2 cot u into 2 cot square u is 4 cot cube u. This completes the problem. Till here we study about Euler's theorem and problems related to Euler's theorem. In next video, we study a third module, that is ordinary differential equation. Hope you all liked the video. Thank you.